Well, Professor Clements with you as we consider problems of reflection and refraction, just reflection in this video, where we're going to have a ray from a laser coming in and striking a mirror. The mirror here is flat to start with, and here's our incoming laser beam. I'm going to label that 1. As it encounters the mirror, I've already drawn in the normal that's perpendicular to the mirror, so this line is our normal, and we're told that the angle of the laser beam from the normal is 22 degrees. So I'm just going to sketch that in here. Again, 0 degrees starts at the normal, so 22 degrees away brings us to the incoming line. The law, well, let's read the rest of the problem. It's always good to read the whole problem before you start working it. The laser stays fixed, so this beam of light is always going to come in as shown on the page. However, the mirror is going to turn, and there's an axis right where this beam of light hits the mirror. So we're going to spin the mirror by 7 degrees. The mirror turns through 7 degrees. When the mirror turns through 7 degrees, the normal remains perpendicular to the new mirror position. So our normal is 7 degrees away from where it was before. I'm showing that with a dotted line. So this would be our second normal, the solid line being the first normal. So the mirror is turned through an angle of 7 degrees. We want to know what is the angle between the first reflected laser beam and the second reflected laser beam. Well, we'll have to put 2 laser beams on here for the reflection. First, when the mirror is at its original position, and later, what's the reflected beam direction after the mirror is turned by 7 degrees? Well, we know that the incident angle is equal to the reflected angle. So if we have 22 degrees for our incident angle, we know that we have 22 degrees for the reflected angle. So I'll use a protractor here and go ahead and lay this on with the center point of the protractor, having my straight edge for the protractor down there. So I have to just mentally read 0 at the normal position, and then 10, 20, and I'll estimate right there is 22. I'm drawing 22 degrees away from the normal on the right to represent the reflected ray. So original beam goes out this way, and again this angle is 22 degrees. Now, what happens when the mirror has turned? When the mirror has turned, the angle to the new normal is now, you tell me, what's the angle to the new normal? And you should be saying into the computer where you're viewing 29 degrees. We were 22 degrees away from the original normal. Our new normal is 7 degrees away from the original normal, so we're 29 degrees away. And now again I have to come in with the protractor, getting my straight edge on the protractor lined up with the new mirror position, and getting the center of the protractor at the place where the ray hits. So now this is 0 degrees, the new normal. I want to go to 29 degrees, so 10, 20, and right about there is 29. So this is my outgoing reflected ray when we're in the case of the mirror that's tilted. I want to know what's the angle between these 2 lines. Well, we can label angles here again. So we have 29 degrees to the new normal across here. Do you see any opportunities for subtraction that could tell us how many degrees between the outgoing beam for case 1 and the outgoing beam for case 2? I'll take a look at how far this outgoing ray for case 2 is away from the original normal, from the first normal. I have 29 degrees to the second normal, this dotted line, and I have 7 degrees from the dotted normal here to the original normal. So I'm 36 degrees away from the original normal. My ray number 1 that's outgoing is 22 degrees away from the original normal. So the two rays are separated by 14 degrees. That would be our answer, 14 degrees. And this is reasonable. I've turned by 7 degrees. The reflected beam changes angular position by 14 degrees, twice the turning angle. That's the behavior of mirrors and reflection. So theta I equals theta R, and the original beam is 22 degrees away from that original normal. It comes out at 22 degrees. We turned the mirror by 7 degrees, so our new normal, normal number 2, is 7 degrees away. That means the incoming ray is now 29 degrees away from the original normal, or sorry, from the turned normal, from the dotted line. And it's 29 degrees away from that dotted line on the right, the reflected ray number 2. Ray number 2 is 36 degrees from the original normal, 29 to the dotted normal, and then 7 degrees to the original normal, so 36 degrees. My ray number 1 was 22 degrees away from the original normal, so 14 degrees for the separation. So that's a calculation. That maybe was with yellow light, some middle of the road light, red light, what have you. What happens if we change the wavelength of the incoming light to 430 degrees, sorry, 430 nanometers? I'll notice this law of reflection. How does the wavelength of the light affect the reflected angle? There is no dependence on the reflected angle, so we get the same result. This is an advantage for mirrors. They reflect light of all colors at the same angle, so the spectrum does not spread out. And as is a problem with lenses, having different colors refract different amounts. With reflection, we always get the same reflected angle regardless of the wavelength. So we could have white light. Let's just ignore the word laser there for a minute. If we would have a ray of white light, all the colors coming in, all the colors would bounce off on when the original mirror position would be on the bounce at ray number 1. When the mirror is turned a little bit, then all the colors would bounce off following the direction of ray number 2. Reflection does not depend on wavelength. That's an important concept. Reflection does not depend on wavelength. So this is just a trick question. When the wavelength is changed, there is no change in the result. So ponder that. Ask your instructor a question on that if you have one.